Welcome to my YouTube channel. Today we are going to look at NECO Physics Practical 2024. This is my own prediction from the specimen we are expected to provide. This is my own prediction. Please drop your own comment. You can ask question why I came up with this. You can add your own contribution. There is still time for the exam. I can still do the video over and over again to explain it further. We were asked to provide two retort stand. This is the first retort stand. This is the second retort stand. And drawing board. You can see the drawing board. One fixed pulley. This is the fixed pulley. This is the fixed pulley. We're asked to provide twine, two hanging masses. I used 20 gram hanging masses. This is the twine. Then a 30 gram mass labeled W. This is the 13 gram mass. And set of masses. So I have different set of masses here. These are 20. I have a lot of masses, so it's good you bring up a lot of masses. We don't know the one that will come up, just like WAEC, what we predicted came out exactly. We used them 5, 10, 15, 20, 25. WAEC brought out exactly the same question with 20, 40, 60, 80 gram masses. So it's good you have a lot of masses, have a lot of it, a lot of masses, so that anyone you are asked to use, you will use it. So provide masses they didn't specify. Let's look at the procedure. Secure the pulley to the top of one of the retort stand. Fix the drawing board onto the drawing paper and attach the drawing board vertically between the two retort stands. Cut a length of twine long enough to pass over the pulley and reach the floor on both sides. Tie the ends of the twine to the mass hanger. Okay, let me show you the procedure from 1 to 4, then we'll come back and see the other procedures. This is a retort stand. Fix the drawing board to the retort stand. Then fix the drawing paper to the drawing board with the thumb pins. This is the mass hangers, the two mass hangers. I'm using 20 gram mass hangers. Then this is the pulley. This is how a pulley looks like, okay? This is a single fixed pulley. This is a single fixed pulley. Then make sure it's tight. I used extra support to hold the pulley so that it will be very tight. Then I have my meter rule. Let's look at the other procedure. We have done 1 to 4. Tie the ends of the twine to the mass hangers, which we did. Attach the 30 gram mass labeled S to one of the mass hanger. One of the mass hanger will carry the 30 gram mass labeled L. Then zero the system by adjusting the height of the retort stand so that the system is balanced and the 30 gram mass is just off the ground. Okay, we are going to do that. Then we'll add 20 gram, 40 gram, 60 gram, 60 gram, 80 gram, 100 gram mass to the empty mass hanger. Then we'll mark on the drawing paper and record the displacement of the mass W as D1. Then record the length of the twine D2, pulled down to lift W. Then we'll use the drawing paper to trace the movement of the masses for each applied force. Okay, at the end, we are expected to plot a graph of D2 against D1. Remember, we want to find the velocity ratio of a single fixed pulley. This is the 20 gram mass. We have to make sure that everything is in equilibrium. Let's zero the system. You can see it. Okay. okay, is fixed and is touching the floor, is touching the ground. Okay, as it's touching the ground now, we'll add, you can see they are in equilibrium at the same level. We'll add the 30-gram mass to one side of the, I would like to open up, if you can buy your single 30-gram mass, I used 20 and 10 as my 30-gram. That's what I have. I don't have a single 30. So if you have it, or you can buy it, I can buy it before the exam too, or I will use 20 and 10. So I will hang it here, hang it on one side. That's the 30-gram mass. Okay, hang it on one side. Then I have to make sure that the system is in equilibrium. When you are doing it, be careful. Don't let this hang, don't let this hold it. Just make sure they are in equilibrium. Let me lift it a little higher. Okay, so I will use this rotor stand to hold it. Let it be in equilibrium. Let it be at the same height. When I used a thread, once you use a thread, this one, the bigger mass will be dragging it. If you use a thread, I tried it with a thread, it was pulling it down. As I was adding weight, it was pulling down. But when I used a twine, let me say, because of tension in the rope, it was able to stay in equilibrium. So I'll put it, make sure it's in equilibrium. We have zeroed the system. Then the next thing is for me to mark off that point, that level on the drawing paper. Okay, carefully mark it off. I want to mark the level where they are in equilibrium. I'll mark it off like this. I would like to mark it off on the other side too. I'll mark it off on the drawing board. Let me mark it off here. This is the equilibrium point. Okay, I've marked the point off on the drawing board. The next thing is to add a mass, 20-gram mass. I'll gently add the 20-gram mass. Add the 20-gram mass. Okay, now I've added the 20-gram mass. The distance moved a little, so I will mark it off. I will mark everything off. Later I will draw the table of value so that I will make the video not to be too long. Later I will mark. So for this one now, I'll remove it and mark it off. That is the height this mass hanger was lifted. Then I'll come to this point as well and mark it off. I'll mark it off. Then the next thing I'm going to do for the 20-gram mass, let me label it 20G, 20G, so that when I'm recording and taking measurement, I will know, because I want to do everything at once. 20-gram. Then this one is for the 20-gram. Now, I will add another 20-gram and see how much the effort will lift the load. This 30-gram mass labeled up should be kept constant throughout the practicals. The only weight you'll be adding is to the other mass hanger. So let me add another weight to the other mass hanger. I will add another weight to the other mass hanger and see the distance moved as well. This is for 40. I will mark it off here, the new distance. Then I will mark off also the distance on this side. So let me write it 40 gram, 40 gram. So this one is for the 40 gram. Then I'll also write for this one the 40 gram. So let me do for 60 gram mass now. I'll put the 60 gram mass. Then get the new distance. And also get the distance here. So I will write it 60 gram. I'll do for the 80 gram mass. And also note it on this other side. Okay, for the last one, okay, let me write 80 gram and then 80 gram. Okay, the 100 gram mass now. Okay, see where the 100 gram mass is hanging. I'll write 100 gram, 100 gram, the single fixed pulley. Let me keep it here so that the drawing board is very necessary to trace. You can trace 20, remember the direction was like this. So we can trace 20, following the direction to 20. It depends on what is expected. Now 40 to 40, 60 to 60, 80 to 80, and so on. But now what I need to record is this distance, the displacement. The displacement, that weight, 30 gram weight, I will label here as D1. This will give me my values for D1. That's for the weight aspect. Then I will label this side D2. D2 is the length of thread pulled. Length of thread pulled. So let me measure from here to here and record up till. So this is how my table of value should look like. Okay, I will be measuring the distance. Then I'll record D1 in cm, D2 in cm for the 20 gram mass, 40 gram mass, and 60 gram mass. So I will take the readings. Let me get the displacement D1 for the 30 gram mass. I'll measure for the 20 gram mass. I'll measure it. I'm measuring from here to here. I have it to be 1.4. That's 1.4. So I will record D1 as 1.40. Then I will check the corresponding one From that point of equilibrium to this one, I have 1.35. Okay, it should be in two decimal place. 1.4, this should not be here. That's 1.40, two decimal places, please. 1.35. Then I will check for the 40. For the 40, we are taking from here to this point. That's 1.56. From 1.56, 1.56, we'll do the same for D2 from here to here. Please make sure your own is better and more straight. This one is 1.35, almost the same thing. 1.3, maybe say 1.36. For the 60 gram mass, we'll measure from here to here. That's 1.5. 1.5. There is two lines, 6, 7. That's 1.7. Then we'll check for D2. That's between from 40 to 60, the displacement from, because of my position in this particular part, is somehow from this to this is 1.4. 1.4. We'll check for between 60 to 80. 2.1. So we can say here is 2.10. Let's check for D2 between 60 and 80. That's 1.6. Okay, we can say 1.50. Then for the last one, 1.6. Then also we'll measure for this. This one is 1.6 as well. Maybe there is error, but we are going to plot it and see the best line of fit that we can get. Remember, this is how I tied it. I made them equal 20, then added the 30 gram mass, to it, and then kept this side constant, was adding masses to lift up this load. So as I was lifting the load, I was measuring the distance here and the distance of the rope pulled down using this P. The load was being lifted with different masses, you take the effort applied here to lift the load. Okay, this is the reading we got, but between 60 and 80, this variation is somehow, let me check what can be the possible error. I've removed the drawing board from the retort stand so that I can have a clearer view of what I want to measure. If you can observe, you see that maybe because of the positioning, that's why it's better to bring it down and mark out everything properly. You can see that between 60 and 80, the lines here are not straight. The lines here are not straight. So let me check from this angle. This side I didn't draw the lines well, they are not straight. Let me remeasure it before I start plotting. Okay, I will rewrite this one is almost close to 2.0. Please, when you are doing your own, make it better, make your own better. Try and position everything well, and they may ask us to trace the direction. Remember, it was moving like this. If you are tracing the direction, the load was moving up, the effort, the length of the thread pulling the rope was coming down. In case we are asked to trace from we don't know the nature of the question, this is just a guide for us to have something in mind and something to practice with. Okay, we are plotting graph of D2 against D1. Okay, we can say graph of D2 against D1. Okay, let this be D2 axis, and let this be D1 axis. So we'll label here D2 in cm and then D1 in cm. Let here be 0. Let's use 0.5. So we are using 2 cm. Scale is 2 cm to 0.5 on both axes. Let's go with that. Then 1.0, 1.5, 2.0, 2.5, 3.0, 3.5. The same way, 0.5, 1.0, 2. Okay, 1.0, 1.5, 2.0, 2.5, 3.0, 3.5, and so on. So we are using 2 cm to 0.5 units. On the D2 axis, we'll check carefully. On the D1, when it's 1.4, remember now the interval between the 0.5 to 1.0 is 0.5. So each line we are taking it to be here is 0.5. This one will be 0.6. You jump one line, 0.7, 0.8, 0.9, then 1.0. So if you have the lines, just leave the first one 0.5, 0.6, leave the next line 0.7, leave the next line 0.8, so you can count the lines in between. So for D1, when it's 1.4, remember here is 1, this is 1.1, 1.2, 1.3, 1.4 is this line, then one line before 1.5. Then this one is 1.35. We'll check 1, okay, 1.35, this is 1, 1.1, 1.2, 1.3, so 1.35 is here. Then D2 is 1.36, then this one is, we can approximate this to 1.6. We'll look for 1. This one is 1.5, so 1.6 will be just leave one line, then 1.6. This one is 1.36. Since here is 1.3, 1.4, so 1.36 is just a little above it. You know, the values are very close, so they won't be too far from each other. Then when D1 is 1.7, somewhere here, this is 1.6, 1.7 is the next one. This one is 1.4. So it will be like on it almost close to 1.5. They are very close. Then we are using 2 here. When it's 2, this one is also 2.1. Let's say somewhere here. Okay, we'll use asterisk. Then 1.6, 1.6. Okay, we can say 1.5, 1.6 is the next line, 1.6 is here. So this is what we have. These the points that we have. So we are going to look for the points that if we can have any 3 points that will pass through the origin. Let's see if we can get any 3 points that will pass through the origin so that we can find the slope. Okay, let's see these 3. These 3 entered and they are okay. You know, there must be error. Nothing is perfect, but thank God we have something like this. So let's take the bigger the triangle, the more accurate your result. So I'm taking this. And I'm taking this point. Okay, so I'm taking this point. Let me calculate the slope. Let me calculate the slope. That's change in D2 over change in D1. I can say change in D2 over change in D1. So D2, let's take this point. That's 3.5. 3.5 minus this one is 1.0 over this one is also 3.5 minus this one is also 1.0. So we are having 3.5 minus 1.0. That's let's say we have 2.5 over 2.5, and that will give us 1. Remember that for a single fixed pulley system, the velocity ratio is 1. But if you do it and you didn't get 1, maybe 0.8 or 0.9, something close, is also very good and acceptable. So remember that for a fixed single pulley, the velocity ratio is 1, but this is what we have. Let me relate it to the theory. Remember that velocity ratio is equal to distance moved by effort over the distance moved by the load. This is the formula for velocity ratio. And now if we are saying let the distance move by the effort, let the distance move by effort be the length of twine pulled. That's the length of the twine, let's say D2, over the distance moved by the load, let it be the distance moved by the weight W. So distance moved by the weight W, that's D for the weight, so which we called D1. Now if we cross multiply for our velocity ratio, we have that D2 is equal to velocity ratio times D1. Remember, if you compare this with the graph, if we compare it with the, let's say y, we plotted y against x. Let's compare it with a straight line equation passing through the origin. That was why I was looking for a point where it will pass through the origin so that there won't be any intercept. The values are too close, so you can have it like this. It then means that the slope of this graph will be the velocity ratio. We plotted D2 against D1 to get the slope. Please share this video, subscribe to this channel, like this video, drop your comments, and always watch our videos as we keep doing tutorials preparing you for exams. Okay, let me mention the precautions. I ensured that the Richter stand were stable during the experiment. I ensured that the pulley and the twine were in good condition. I ensured that I avoided error due to apparatus while taking readings on the meter rule. Please use a twine. When I used a normal thread, the heavy mass was pulling the other weight, so I had to look for a twine to get what I just did. Thank you.